So when I started teaching, I basically did what my teachers did to me, and I got feedback on the quality of the work I delivered through the end of semester questionnaire and through my students' performance on the assessment that I gave them. Now, I taught a introductory physics class for pre-meds. These were not students who wanted to learn physics. So in general, they gave their physics teachers rather poor reviews, to put it mildly. But not so for me. They gave me very nice feedback. And they did well on what I consider to be complicated problems. So for many, many years, I lived in this illusion of being a good teacher based on just those two simple data sets. So in 1990, I read about the Force Concept Inventory, also known as the FCI, which is an instrument that measures students' understanding of Newtonian mechanics, which is a subject that's taught in the second week of a typical introductory physics course. And the concept of force is very basic in physics. If you don't understand force, it's very hard to make sense of anything that comes after that second week. The FCI was developed by David Hestenes at Arizona State University, and through a series of multiple choice questions, test students' understanding of this concept of force, as the name suggests. And he showed that there was not much difference in students' performance on this FCI before they took physics, introductory physics, or after. I saw those results. I thought, that can't be true. I'm a scientist, however, so you learn not to just make such statements. So I thought I'd better show it that in my class at Harvard, things were different. So I gave it to my students and almost immediately tumbled out of my ivory tower, because as soon as they'd started, one student raised her hand and she said, "Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things?" That was really a turning point in my teaching career. So when the results came in, it became clear that my class was not very different from any other classes, and that in spite of my high ratings, in spite of my students' pretty good performance on textbook problems, their performance on the FCI was pretty miserable. And that became a soul-searching moment for me. At first I thought, what? Maybe I'm not the great teacher I thought I was. And after discarding that option, I thought maybe there's a problem with my students. But at an institution like mine, that's hard to claim. Then I started questioning the test. I thought there must be something wrong with the FCI. It's a trick test. It just doesn't give a valid result. And I started doing some testing of my own. I decided to compare students' performance on textbook problems, the one I used to assess them, with their performance on a word-based problem on exactly the same subject. And what I discovered was that the students were perfectly able to do the textbook problem, but they stumbled onto this word-based problems that most of my colleagues thought were trivial. The reason is, of course, in hindsight, the reason is obvious. The students had memorized the procedure to solve problems, were doing the textbook problems flawlessly because of that, but without any meaningful understanding of the subject. So that's when I realized that most of education focuses on information transfer. In essence, I was reading the book to the students. But the hard part in education is not the transfer of information. It's the making sense of information. And in the standard approach to teaching, that happens outside of the classroom, right? The professor focuses on delivering the information, and the student goes home and works on making sense of it. If you ask yourself which of the two is the hardest part, I think we'd all agree it's that making sense. And that is something that needs to happen in the minds of the students. It's not something that the instructor can do. So that's when I decided to throw the information transfer out of the classroom. I had the students read a book or do a project or watch a previously recorded lecture. And then in class, I work on helping the students assimilate that information, making sense of it, by basically teaching by questioning rather than teaching by telling. So in essence, the FCI got me to completely rethink my approach to teaching and made me realize that by basically focusing on regurgitating the textbook in front of the students, I was not accomplishing very much. After they saw the results of the FCI, my students were just as shocked as I was, and they essentially requested that I organize a session where we'd go through each and every question on the FCI. And I remember vividly explaining one question that I thought was rather trivial to my students by making some drawings on the board. And after giving what I thought was my best shot at it, I turned around only to see that they were completely confused. So I asked them, is there a question? They were so confused they couldn't really articulate a question. So I thought, this is serious. I better try a little bit better, a little bit harder to explain this. I raised the board. I, for probably 8 minutes, gave what I thought was, the best possible explanation of this concept. After 8 minutes, I turned around and they looked even more confused. And they could still not articulate a question. I was, I didn't know what to do. I'd done my best. I knew of no better way of explaining it than what I'd done. From the results of the FCI, I knew that about half of them had gotten the answer on that FCI right. So, in the spur of the moment, I don't know exactly what got into me, I said to them, why don't you discuss this question with your neighbor? And something happened that I'd never seen in my classroom before. Total chaos erupted. They all started talking. And most surprisingly, in 2 minutes, they figured it out. Of course, they figured it out because there were so many parallel discussions going on, and the students were able to address the many difficulties that they were facing much better in parallel than I would have been able to do as a single instructor. And that's basically how the idea of peer instruction was born. Peer instruction is a process where I basically leverage the knowledge that the students have already acquired. So I walk into a classroom, I talk a few minutes, I may summarize the results of the pre-class assignment, and then I start asking questions. I put a question on the screen. I have the students think about that question individually and commit to an answer, which they can communicate to me through the devices or through clickers. Or initially there was no technology at all for this approach to teaching, so I basically had the students write it down. And after collecting the responses, before there was technology, I used scanning sheets in case you wonder how I did this without technology. After I've collected the responses, I tell the students, find a neighbor who has a different answer and try to convince that neighbor of your answer. So you have to imagine 250 students all talking to one another, complete chaos. They're no longer focused on me, the instructor, in front of the classroom. They're focused on each other and themselves. And what happens in the case that there are sufficient right answers before they start talking to one another is that the students with the right answer effectively convince the students with the wrong answer on average. And the correct number of responses grows dramatically. And while it grows dramatically, the understanding grows too. The reason that this method works is actually very simple. Suppose you have two students sitting next to each other. I'm sitting in the classroom and I don't have the right answer because I don't understand everything yet. My neighbor here next to me has the right answer because she, recently had this aha moment thinking, I get it. On average, she's more likely to convince me than the other way around, simply by the force of logic. But more importantly, she's more likely to convince me than the professor in front of the class, because she is still aware of the conceptual difficulties that I have. Whereas the professor learned it such a long time ago, to him everything is so clear that he's unaware of the mental blocks that I have. So in just a few minutes, and also because of all this parallel, tasking in a sense, it's multitasking, right? Each group is working on their own little problems, something that I, as a professor in front of the class, would never be able to do. The very first time I implemented this method, I found two things. One is students were much more actively engaged. I mean, you could see it right away in the classroom. Secondly, I found that the very first time that I implemented, the learning gains doubled. And as I improved my technique, over the years, those learning gains eventually ended up tripling. So tremendous learning gains improvements on the FCI and by other metrics too, but just by the FCI only, or the factor of 3, and much more engagement of the students. So I realized very quickly that it would not be enough to show students' improvement on the FCI. After all, I had questioned the validity of the FCI, so I expected my colleagues to do the same thing. And therefore, I decided it would be important to also show how my students' performance on standard textbook problems was changed, if any. And it turned out, somewhat to my surprise, because I thought, at best it remains the same, but actually it improved. And it improved quite dramatically, which shows something that in hindsight is quite obvious, that better understanding leads to better problem solving. So by looking at the data on a broader scale, and connecting it to graduation rates, retention in courses, and so on, we found a number of other very interesting things. For example, we found that far more students stay in the major, well, first stay in the course, and then stay in the major, when just one course is taught using peer instruction, as compared to the standard approach to teaching science. We also found, and I find this truly interesting, that this method helped close the gender gap between female and male students. And we found some similar type of improvements with some, but not all, minorities. So clearly, the approach benefits more than just the learning. It benefits the retention of the students in the courses, it benefits the retention of the students in STEM majors, and it helps close a gender gap that shouldn't be there in the first place. So assessment has two purposes. One is to motivate the students to learn. The other one, which comes through the grade, right? The other one is to provide feedback on the learning, and for students as an opportunity to improve their learning. In many courses, there might be one midterm and one final, or even worse, one cumulative final. Students end up studying not in order to learn, but studying in order to pass the exam. And the feedback that they get is usually not timely. It comes too late. I mean, just take the final exam, right? There's not much you can do about it once you've had that final exam. So I think it's crucial that the student get continuous feedback on their learning. And peer instruction is such a way, because you're constantly answering questions in class, non-stop. Answer, answer, answer. And each time you answer a question, you get feedback on your learning. Also, because it doesn't factor into the grade, students can take risks, they can stick out their neck, which is important because we don't want to stifle creativity, innovation, and so on. And they also get to continuously assess their own learning and obtain feedback on it. So one of the things I've learned is that I should not be relying on my instincts. And in hindsight, as a scientist, I should have known better, because as a scientist, you don't go by gut instinct, you go by quantitative data. Now, it's kind of interesting that most scientists have no trouble abandoning the scientific method when it comes to teaching and rely purely on anecdotal evidence. But as Lee Shulman, former president of the Carnegie Foundation and professor emeritus at Stanford, once said, the plural of anecdote is not data. So now, rather than basing myself on these rather simple metrics, these rather simple one-dimensional metrics, I collect a lot of data. In a sense, I see my classroom as a laboratory for improving instruction, and I collect whatever data I can get. I collect data on the students' in-class performance, on questions I ask. I give the students a number of different assessment instruments that don't factor into their grade, but that factor into my assessment of the quality of the instruction we deliver. I give them different types of assessment, from project-based work to collaborative exams and to reflections on their homework, trying to measure these students along more than one dimension rather than just that simple single dimension, how well can you solve textbook problems.